Let us continue boron family. In the boron family, we will discuss diborane. Diborane we will take. We will see the structure of diborane. First formula of diborane is B2H6. This diborane on methylation gives B2H2Me4. This diborane on methylation gives B2H2Me4. That means 4 hydrogens undergo methylation. That means 4 hydrogens are replaced by methyl groups. Rest of the 2 hydrogens are intact. They are not converted, they are not going for methylation. That means out of 6 hydrogens, 4 hydrogens one type, remaining 2 hydrogens another type. So that in diborane, all the hydrogens are not in the same environment, same chemical environment. In diborane, 4 hydrogens are one type, other 2 hydrogens are another type. Now, the hydrogens which undergo methylation, they are under normal condition, normal hydrogens. Normal means what? Normally, how the chemical bond will be formed, how the covalent bond will be formed. 2 electrons will be there in the bond, and that 2 electrons will be shared by both atoms. Like that will be there. Okay, so 4 hydrogens coming under such a type. Remaining 2 hydrogens are in different type. So, in order to explain this diborane is considered like this. In the diborane, central atom boron is considered. That electronic configuration, let us consider that electronic configuration. Now, in the ground state, 2s is having 1 orbital and 2 electrons. 2p is having 3 orbitals and 1 electron. From boron, we will take 1 2s orbital and 3 2p orbitals. 3 2p orbitals we will take. Let us intermix them. Let us intermix them. We will get 4 sp3 hybrid orbitals. 1 2 3 4. 4 sp3 hybrid orbitals. Here totally 3 electrons present in the valence shell. Let us distribute those 3 electrons as single electrons like this. 1 orbital we will keep it as vacant. This orbital we will keep it as vacant sp3 orbital. Okay, here 3 electrons are there. Those 3 electrons we have filled singly. 1 sp3 orbital we have left vacant. Okay. Now in the boron we will take 4 sp3 orbitals. It is the nucleus of boron. This is 1 sp3 orbital. It is another sp3 orbital. Next sp3 orbital. Next sp3 orbital. In the 4 sp3 orbitals for boron we have given. Here it is having unpaired electrons like this. 1 sp3 orbital is vacant. 1 sp3 orbital is vacant. So in the boron sp3 hybridization is possible. So we have written 4 sp3 hybrid orbitals. The valence shell of boron is having 3 electrons. Those 3 electrons we have given as 1 electron for 3 orbitals. 1 orbital is vacant like this. In the same manner, let us take another boron nucleus. It is 1 sp3 orbital, another sp3 orbital, third sp3 orbital, fourth sp3 orbital. Now this 3 electrons, 1 electron, second electron, third electron for boron. It is sp3 orbital vacant. Next, 6 hydrogen atoms are there. 1 hydrogen atom will give here 1s1 hydrogen. Here 1 hydrogen atom will give 1s1, 1 electron. Here 1 hydrogen atom, 1s1, 1 electron. Here 1 hydrogen atom, 1s1, 1 electron. Here 1 hydrogen atom, 1s1, 1 electron. Here one hydrogen atom, 1s1, 1 electron, like that we have given. Now this sp3 orbital, boron, this sp3 orbital, hydrogen, this 1s orbital undergo linear overlapping, that means end on end overlapping and gives sigma bond. Okay, so boron, this boron sp3 orbital, this 1s orbital of hydrogen overlapping to give the bond. This is normal bond, sigma bond. In the formation of sigma bond, boron gives sp3 orbital, hydrogen gives 1s orbital. In the same way, this sp3 orbital, this 1s orbital undergo end on end overlap to give sigma bond. That sigma bond we will write. It is also sigma sp3s. Next, here boron, this sp3 orbital, this 1s orbital undergo end on end overlapping to give like this bond. Okay, it is also sigma sp3s. In the same way, boron, this sp3 orbital, hydrogen, this 1s orbital overlapping, end on end overlapping to give sigma bond, give sigma bond like this. Next, boron, this vacant sp3 orbital, hydrogen, this off filled 1s orbital, boron off filled sp3 orbital, intermixing to form bridge bond. How that intermixing will be there, that we will see. Boron sp3 vacant sp3 orbital, this boron off filled sp3 orbital, hydrogen 1s orbital, these three orbitals intermixing with each other. Now see, this boron vacant sp3 orbital, hydrogen off filled 1s orbital, boron off filled sp3 orbital, the year undergoing overlapping simultaneously. These three orbitals overlapping simultaneously to form BHB bond. Here 2 electrons are there. In the formation of this bond, how many orbitals involved in bonding? In the sense, 3 orbitals involved in overlapping. Number of electrons involved in bonding is 2. Here in this overlap, 3 orbitals involved. What are those 3? Vacant sp3 orbital of this boron, off filled 1s orbital of this hydrogen, off filled sp3 orbital of this boron. So 3 orbitals involved in bonding, but number of electrons involved is 2, this bond. Okay, in the same way, this side also say in the same way. Here this off filled sp3 orbital of this boron, here from this boron off filled sp3 orbital, from this boron vacant sp3 orbital, from this boron vacant sp3 orbital, this hydrogen off filled 1s orbital, hydrogen off filled 1s orbital. Now number of electrons involved is 2. So in this bond formation, this boron is providing off filled sp3 orbital, this boron is providing vacant sp3 orbital, hydrogen is providing off filled 1s orbital, so now BHB bond is formed. Okay, so now we will see this one. In this bond, in this sigma bond, this boron is giving vacant sp3 orbital, this hydrogen is giving 1s orbital, this boron is giving off filled sp3 orbital. Okay, sigma sp3s sp3, this bond. Okay, so how the structure of diborane will be there, that we will see. Now here 2 boron atoms. Now here normal hydrogen, this bond is formed by 2 orbitals overlapping and 2 electrons involved, therefore normal bond. It is also normal bond, this normal bond, this normal bond. Next bond is this bond is formed by 3 orbitals overlapping but 2 electrons involved. This is called bridge bond. This is BHB bond. In the same way, another BHB bond like this. So this bond, it is a BH bond, this formed by boron providing sp3 orbital, hydrogen providing sp3 orbital. This is sigma bond. This bond is a BHB bond. It is sigma bond. Boron is providing vacant sp3 orbital. Hydrogen is providing s orbital. This boron is providing off-filled sp3 orbital. This is called banana bond or tau bond. Banana bond or tau bond, we can say. Sorry. What is the geometry of this molecule? That we will see. In the geometry of this molecule, in the diborane, this BH2 group, and this BH2 group are in same plane. So this diborane contains two BH2 groups. They are coplanar. This BH2 group and this BH2 group. This diborane contains two BH2 groups. These two BH2 groups are coplanar. Okay. In the diborane, it is BH2 group. So in the diborane, two BH2 groups are there. These two BH2 groups are what we can say in the sense coplanar, we can say. So that means these two BH2 groups are in one plane. Let us consider these two BH2 groups are in a plane of the screen. We can consider. Then this hydrogen is above the plane. That means above the screen. Then this hydrogen is below the plane. That means below the screen. This hydrogen is below the plane. That means below the screen. So in this diborane, two BH2 groups are there. It is one BH2 group. It is another BH2 groups. Two BH2 groups are there. These two BH2 groups are coplanar. That means both this BH2 group and this BH2 group, both BH2 groups are in a plane of the screen. This hydrogen acting as a bridge between these two borons present above the screen, above the plane. This hydrogen is connecting to these two borons, acting as a bridge. This hydrogen present below the screen, below the plane. Like this it will be there. Okay, this is about the diborane. Now see, the chemical environment of this BH bond and this hydrogen, this bond is entirely different or not? This is normal bond, but this is not normal bond. Therefore, when this diborane is taken for methylation, these two hydrogens goes for this hydrogen is going for methylation. Like this, how many hydrogens are there? 1, 2, 3, 4. These 4 hydrogens are of one type, whereas these two hydrogens are different from this. So these two hydrogens are of a different type. So that in diborane, two types of hydrogens are there. One is terminal hydrogens, another one is bridge hydrogens. It is bridge hydrogens. Bridge hydrogens are having different environment. Terminal hydrogens are having one environment. So the terminal hydrogens going for methylation, whereas bridge hydrogens are not going for methylation. So that diborane on methylation gives B2H2Me4, not B2Me6. Okay, because the bridge hydrogens behave differently from terminal hydrogens. Okay, now we will see how to prepare diborane. That we will see. Preparation of diborane, we will go for preparation of diborane. Now we will take boron trifluoride. We will take boron trifluoride BF3. That we will treat with lithium aluminum hydride LiAlH4. We will give the solvent diethyl ether. Diethyl ether is a solvent. Diethyl ether solvent we have given. What is the reaction takes place here? That we will see. Now BF3 will take. BF3 we are taking like this. Boron is coming under group number 3A. So this valence shell contains 3 electrons. Therefore, it forms 3 normal covalent bonds. 3 normal covalent bonds it forms. Then lithium aluminum hydride we will write like this: Li plus AlH4 minus. This AlH4 minus we will write like this: AlH4 minus we will write like this. AlH4 minus we will write like this. Okay, Li plus AlH4 minus Al we have written, and 4 hydrogens we have written with the single bonds. Now this hydrogen takes the bond and attacks this boron. This bond is shifting to fluorine. Okay, therefore this fluorine is leaving. In the place of fluorine, hydrogen comes, so that we are getting diborane. BH6 we are getting. So we got diborane, we said. Then lithium, this lithium takes this F minus and becomes lithium fluoride, and this aluminum takes fluorine and becomes AlF3. AlF3 like this. So what is the balanced equation for this, that we will see. Boron trifluoride BF3 with lithium aluminum hydride LiAlH4. Diethyl ether is the solvent. Diethyl ether is the solvent. We are getting diborane BH6. Lithium takes fluorine and becomes lithium fluoride. Al takes fluorine and becomes AlF3. Let us balance this equation. BF3 will take 4 times, and diborane will take 2 times. Lithium fluoride 3 times. Lithium fluoride 3 times. AlF3 3 times. AlF3 3 times. Lithium aluminum hydride 3 times we will take. Now it is balanced or not, see. And hydrogen will check 3 4s are 12. Here 2 6 are 12. Okay, balanced. Next reaction will take BF3. Instead of lithium aluminum hydride, we will take sodium hydride. Solvent, and temperature will provide 450 Kelvin. Temperature we have provided 450 Kelvin. How the reaction takes place, we will see. Here BF3 will write. BF3 we have written. And the sodium hydride will write Na plus 1, H minus 1. Sodium hydride we have written. How the attack will be there, we will see. This H minus is attacking this boron. This bond is shifting towards fluorine. Boron is taking hydrogen and becomes a diborane. Diborane BH6. Then sodium takes this Na plus takes F minus and becomes NaF. Okay. So BF3 combines with the NaH and gives a diborane. We said it is industrial method of preparation. We will balance. It is 2 BF3. It is 6 NaH, 6 NaF. We have balanced this. Next reaction we will see. Sodium borohydride NaBH4. Sodium borohydride with iodine gives what we will see. Here what we are getting, in the sense we are getting diborane BH6. How we will see. Sodium borohydride we can write it as Na plus BH4 minus. BH4 minus we can write like this. Now I2 iodine will write like this. Now here what happens means, in this diborane, boron electronegativity is 2. Boron electronegativity is 2. Hydrogen is 2.1. Therefore, oxidation number is -1 for this. This -1 becoming 0. That means oxidation. That means hydrogen gas we are getting. This iodine, this 0 is converting into -1. -1 and this Na plus becomes sodium iodide. Now this hydrogen leaving, in the sense here what is there means BH3 is there. This BH3 in the dimeric form is called diborane. Okay. So sodium borohydride with iodine, this H minus undergoes oxidation and becomes hydrogen gas. This iodine undergoes reduction and becomes I minus like this. Then we are getting what, in the sense this diborane we are getting. Okay. So sodium borohydride is reacting with iodine to give diborane and a hydrogen gas and a sodium iodide. This is laboratory method of preparing hydrogen gas. Then, what are the properties of diborane that we'll see? Diborane is colorless and a highly toxic gas. Highly toxic gas. Okay. Then diborane and higher borines and other higher borines are flammable in air. That burning is spontaneous. That burning is spontaneous process. So, diborane burns with air. That reaction will see. Diborane burning with air. That reaction will see. Diborane with oxygen. Okay, burning with oxygen. This boron becomes +3. Boron is in +3 oxidation state. That +3 we have written like as it is. This undergoes reduction and becomes O2 minus. This undergoes a reduction, we said, therefore it is undergoing oxidation. This oxidation number is -1. It is undergoing oxidation, therefore it will become H+1. It is -1 is converting into H+1. This oxygen undergoing reduction and becomes O2 minus. Here cross multiply, we will get B2O3. Here cross multiply, we will get water. Okay, so this oxygen undergoes reduction and becomes O2 minus. This hydrogen undergoes oxidation and becomes H plus. We are getting B2O3 and water we are getting. Let us balance the equation like this. Now for this delta H is -1976 kilojoule per mole. It is exothermic process. So and so amount of heat is liberated here. This much amount of heat is liberated here. Okay. Therefore, this diborane is used as a aircraft fuel. We are using diborane as a aircraft fuel. Next, diborane undergoes hydrolysis. That reaction we will see. Diborane undergoes hydrolysis to give what substance, what product, that we'll see. Now, in the diborane, boron is +3. Here, hydrogen is -1, H -1. This H -1 takes H+1 from here. Here H -1 takes H+1 from here and becomes what in the sense hydrogen gas. Hydrogen gas. This boron takes OH minus from water. It is positive cation, therefore takes OH minus from water and becomes BOH thrice. BOH thrice is called orthoboric acid H3BO3. Now let us balance. Boron is 2. Hydrogen is 6, water is 6. Like this will balance. Okay, because 6 times -1 will take 6 times H plus. Therefore, 6 times H2 gas. Therefore, diborane on hydrolysis gives orthoboric acid and a hydrogen gas we can see. Then, diborane acts as a Lewis acid because it is electron deficient. So, it will react with Lewis bases. How that reaction will be there, that we'll see. So, diborane will take Lewis base will take NMe3 trimethylamine. Trimethylamine will take, what is the reaction possible we'll see. Now first we'll take diborane. Diborane structure will draw. Diborane structure is like this. Diborane structure is like this. Trimethylamine. Trimethylamine structure we are writing. Trimethylamine structure. Now this nitrogen is a donating lone pair to this boron. Therefore, this bond pair is shifting here. So what we will get, we will see here. Here hydrogen, hydrogen, boron, hydrogen. Here hydrogen. Here bond is there. Boron, hydrogen, hydrogen. Here NMe3. NMe3. Okay. Now we will give negative charge to this. We will give positive charge to this. Because it is a donor, it is acceptor. Therefore, negative charge for this, positive charge for this we will give. Now, actually, we should not give negative charge here. Why? Because this bond is shifting. Therefore, we need not give negative charge. Let us give negative charge to this boron. Next, what will happen means this bond will shift. This bond will shift. Before that, NMe3 is attacking. Trimethylamine is attacking. Trimethylamine is attacking this boron. This bond is shifting. So that we will get a BH3, NMe3, BH3, NMe3. Nitrogen is a donor, therefore +1. Boron is acceptor, therefore -1. So and so addition compound will be obtained. Okay. So diborane is treated with a trimethylamine. We are getting a so and so BH3.NMe3. So and so we are getting this compound. We are getting this will take 2 times. This will take 2 times. We are getting so and so compound. Next, diborane with carbon monoxide. How the reaction will be there, that we'll see. Instead of trimethylamine, I will take carbon monoxide now. Instead of trimethylamine, carbon monoxide. Now, diborane with carbon monoxide. How the reaction will be possible, that we'll see. So diborane will take like this. And the carbon monoxide will take like this. Carbon monoxide. Now, in the same way, how diborane and trimethylamine reaction is there like that. It is attacking this boron. It is going like this. Therefore, here also you will get BH3Cu. Okay. Boron carbonyl. This name we can say boron carbonyl. Boron carbonyl. So boron carbonyl we can write like this. It is BH3. It is Cu. Here positive charge, here negative charge. Trimethyl borane we have given like this. Then with ammonia, how the reaction will be there? Diborane with ammonia. How the reaction will be there, that we'll see. Diborane with ammonia. With ammonia, how the reaction is possible? That point we'll see. Now, we are taking diborane. Now ammonia we will take. Ammonia we are taken. Here lone pair is set. Now, in the formation of this bond, this boron is providing vacant orbital. We will take. This boron is providing half filled. This hydrogen is providing half filled. Now nitrogen is contributing electron pair. This becomes like this, like that. We will take. So we'll write here NH3. Here it is a dative bond. Okay. Here, due to shift of this bond for this boron, no loss because it has provided vacant orbital only. Due to coming of this bond for this boron, no gain because it has contributed of 1 electron. It has contributed 1 electron, that 2 electrons present in this bond. Okay. Now we will write this dative bond as normal covalent bond. This dative bond we will write it as normal covalent bond, while we will give formal charges. For nitrogen we will give +1, for boron we will give -1. Okay. Next we will take ammonia. Next we are taking ammonia. This ammonia is coming for attack. This ammonia is coming for attacking this one. How that reaction takes place, that we will see. Now this nitrogen is attacking the same boron will take. This bond is shifting completely, will think like this. Now what we will get, we'll see. This boron will write that 2 hydrogens. Here dative bond with ammonia. Here already ammonia is there. Here +1 is there. Here -1 is there. That we will write. This we will write BH4. BH4 we have written. Now you see that this boron has provided vacant orbital here for the formation of this BHB bond. That means here it has provided off-filled orbital. Okay, that means this bond is shifting means for this loss of one electron. Okay, for this loss of one electron means this -1 we have to vanish. Okay, so we are vanishing this -1. For this boron, this bond is coming means one electron gain. Therefore, for this we will give -1. Okay. Now, this dative bond we will write it as a normal covalent bond. While we will give formal charges, we are giving formal charges now. Here -1, here +1. Okay. So this diborane B2H6 reacting with ammonia at lower temperature to give what in the sense complex. One complex is BH2 NH3 twice plus cation. This is having +1, it is having -1, it is having +1, net charge is +1. This is BH4 -1. This we can say BH4 -1. Okay, so diborane reacting with ammonia at low temperature to give complex. The cationic complex, cation is complex, anion also complex. The cationic complex is BH2 NH3 twice plus, anionic complex is BH4 minus. Okay, simply we can write it as this equation as B2H6 with ammonia at low temperature to give what in the sense B2H6 dot 2NH3. Like this also we can write. But this B2H6 dot 2NH3 is in a complex form. This complex is BH2 NH3 twice plus cation, anion is BH4 minus anion. Like this complex form it will be there. Then this complex on further heating to 200 degrees Celsius, it gives a borosol. Okay, this complex, that means this one on further heating to 200 degrees Celsius gives what compound in the sense of borosol. Okay, that we'll see. Now the complex will take B2H6.2NH3. This complex exists in the form of what in the sense cation, that is cation is BH2 NH3 twice plus, anion is what means BH4 minus, anion is BH4 minus. This we can write in the form of complex like this. This complex is heated to 200 degrees Celsius. This complex is heated to 200 degrees Celsius. What we are getting means borosol B3N3H6. We are getting what means borosol we are getting. Borosol we are getting. Then we are getting hydrogen gas. We are getting hydrogen gas. We are getting borosol and we are getting hydrogen gas. So, now, how we are getting hydrogen gas? That we'll see. Before that, we'll see borosol chemical formula. We'll see borosol structure. We'll see. Then we can say how hydrogen gas is liberated. We can see. Now, borosol chemical structure. We'll see. Borosol chemical structure is same like benzene. How benzene is there? Like that, this borosol structure is there. So we'll write a boron atoms. We'll write in a like this. We'll write in between boron atoms. Let us write nitrogen atoms. In between boron atoms, we are writing nitrogen atoms. Then we'll give hydrogens now. For each boron and each nitrogen, one nitrogen will give. Because 6 hydrogens are available, for each nitrogen you give one nitrogen, for each boron you give one nitrogen. So next we will give the bond between boron and hydrogen, one bond will give. Between nitrogen and hydrogen, one bond will give. Then between boron and nitrogen, one bond. Between boron and nitrogen, one bond. Okay. Boron valence shell is having 3 electrons. Those 3 electrons involved in bonding here, 3 bonds formed. Now boron is having vacant orbital. In the boron, vacant orbital is there. In the boron, what is there means vacant orbital is present. Then nitrogen is having, nitrogen comes under 5th group. Therefore, this valence shell contains 5 electrons. Out of 5 electrons, 3 electrons have gone for bonding, remaining 2 electrons present. So, nitrogen is contributing lone pair, boron is contributing vacant orbital. Between them, dative bond is possible. So, dative bond is possible from nitrogen to boron like this. Nitrogen to boron like this, dative bond is possible. This dative bond, we can write it as normal covalent bond by giving formal charges. How we are writing? See here we are writing like this. We have written like this. Now we will write formal charges. Boron is acceptor -1, nitrogen is donor +1. Boron -1, nitrogen +1. Boron -1, nitrogen +1. We have written like this. The structure is just like benzene, therefore this is called inorganic benzene, we can say. This borosol, another name is inorganic benzene. For this, another name is given borosine. Borosine. This compound is a volatile compound. This compound is volatile compound, we can say. Now, nitrogen electronegativity is 3, hydrogen electronegativity is 2.1, therefore it is +1 oxidation number. This is -1 oxidation number. That means it is not -1, actually it is -3 will come. Okay. So anyhow, this hydrogen oxidation number is +1 here. Therefore, but here hydrogen oxidation number is -1. In this place, hydrogen oxidation number is +1. Therefore, this -1 is converting into +1. But for this, no, it is -1 only. This -1 is converting into what in the sense +1 we can say. Therefore, it is undergoing what in the sense oxidation. Here hydrogen is here hydrogen is +1. It is converting into what in the sense 0. That means reduction. This hydrogen +1 is converting into 0. That is reduction. Okay. Now we can write. We can balance this equation. Here we'll take this is 3 times. This is 2 times. This is 12 times. Now we will check. Here hydrogen. This is 1 borosol contains 3 hydrogens. That means NH bonds. 2 borosol means 6. That means 6 H minus 1 is converting into 6 times H plus 1. That means losing 12 electrons. Here this H plus 1 is converting into H0. Okay, this H plus 1 is converting into H0. Okay, H0. Here 12 H2 we have given. 12 H2 we have given. That means 12 H2 means 24 hydrogens. That means 24 electrons lost. 24 electrons lost. 24 electrons lost here. That means then we can say here lost is 24, gain is 12. Then what is the oxidation number this hydrogen should have? That we should know it. Then we will see this nitrogen first. This nitrogen oxidation number we will see. This nitrogen oxidation number we want in the sense, let us shift all the bonds towards nitrogen. Then we'll get nitrogen is a -3. We'll get this bond we have to shift to boron only. This dative bond we have to shift to boron because it is contributing. So because of this sigma bond for this +1, for this sigma 1 +1, therefore +2. For this dative bond it is getting -1. Therefore here +1 is there. Here what is that means +1 is there. Therefore here -1 should be there, isn't it? Therefore what shall we do in the sense, here we'll take a last is 24 electrons. This is how many will take means 6 will take. 6 will take. and here H minus is converting into 0 we will take H minus into 0. How many we will take in the sense 6 will take here 6 if you take how many electrons we are getting 12 electrons we are getting, isn't it? 12